This video is going to be part 2 to reaction kinetics, and today we'll be specifically looking at collisions and enthalpy. So first, starting with collisions, in order for a chemical reaction to occur, there needs to be collisions between the reactants which turn them into products. And the difference between an effective collision and an ineffective collision is that in order for an effective collision to happen, there needs to be two main things. And these two things are favorable geometry and sufficient kinetic energy. So, to demonstrate this, let's take a look at these two diagrams. If we look at this first one here, let's say that these two pieces are reactants. If the orange piece right here wants to move into this space, then it needs the correct geometry and sufficient kinetic energy. So let's see what happens if it doesn't have one of these things. If it doesn't have enough kinetic energy, then this orange piece simply wouldn't even move into this spot. If this orange piece doesn't have favorable geometry, like you can see here, even if it did have enough kinetic energy to go into this spot, it would not fit right, and therefore a reaction would not occur. So with this diagram here, we can see that if this orange piece does have enough kinetic energy to move into here, and it has the favorable geometry, and therefore it will fit perfectly and a reaction will occur. Moving on, let's learn some definitions. First, what is enthalpy? Enthalpy is the total amount of energy in a system. This means that it includes both the potential energy and the kinetic energy. Enthalpy is written with the symbol H. Moving on, what is activation energy? Activation energy is written as E lower subscript A. So activation energy is the minimum amount of energy required for a specific chemical reaction to occur, or the minimum energy needed to change reactants into an activated complex. Now you may be wondering, what is an activated complex? Well, the activated complex is where the reactants are in the middle of breaking and forming bonds. This means that there are partially broken and partially formed bonds in the activated complex. It is high energy, which means that it is very unstable. This definition will make more sense once we draw some enthalpy graphs. Next, let's take a look at endo and exothermic reactions. An endothermic reaction is a reaction that gains enthalpy. This means that the enthalpy value is positive. In an endothermic reaction, energy is on the reactant side. An exothermic reaction, however, is a reaction that loses enthalpy. This means that the H value is negative. In an exothermic reaction, energy is on the product side. The way that I like to remember the difference between an endo and exothermic reaction is that in exothermic reactions, it has X, which is the start of exit. And in an exothermic reaction, enthalpy exits the reaction. So moving on, how do we calculate the change in enthalpy during a reaction? Well, this is delta. This triangle is delta. Remember, it means a change. So the change in enthalpy is the enthalpy in the products versus the amount of enthalpy in the reactants. Moving on, let's look at some energy profiles and enthalpy graphs. Let's draw out an exothermic reaction graph. So as you can see, on the x-axis we have the progress of a reaction, and on the y-axis we have enthalpy. So this is what it looks like. Let's now label some things and then I'll explain them. If we took a look at what's written in red, we have the activation energy. As you can see, the activation energy is how much enthalpy starts at the reactants all the way up to the activated complex. And we need to be careful here because this is the activation energy of the forward reaction. Because as we will learn later on that there are reverse reactions. So the activation energy of the reverse reaction is from how much enthalpy the products have all the way up till the activated complex. Next, the activated complex itself. We can see that it is the tippity top of the graph. This is where the reactants are turning into the products and it's very unstable. The reactants need to get over this hump in order to become products. Next, in green, we have our enthalpy. This is the enthalpy change. Note the triangle delta. As you can see, it goes downwards. And this is because the difference in enthalpy from the reactants to that of the products enthalpy is lower, which means that this reaction has a negative enthalpy change. And remember, a negative enthalpy change means that we are losing enthalpy in this reaction, which makes it an exothermic reaction. And in an exothermic reaction, heat is absorbed by the surroundings, so the surroundings feel warm. Next, let's take a look at how to draw an endothermic reaction. So this graph looks very similar to the exothermic graph, but it seems like it's reversed. The enthalpy of the reactants are lower than the products. This means that this reaction has a positive enthalpy change. This means that it absorbs heat. Heat is absorbed from surroundings, and therefore the surroundings feel cool. Finally, let's take a look at what happens with the addition of a catalyst. Let's take the example of an exothermic graph. This is the normal path that it would take, but with the addition of a catalyst, this is what the path looks like. As you can see, the enthalpy of the reactants and the products stayed the exact same. The only change is the activated complex. In the original one, it's here, but with the catalyst, it's here. It is much lower. And with the change of the activated complex, that means that the activation energy also changes. In the uncatalyzed reaction, this is the activation energy. But with our catalyzed reaction, the activation energy is here because it aligns with the new activated complex. And so basically, catalysts create alternate reaction paths with a lowered activation energy, and this increases the reaction rate.